All right, I'm going to show you how to create interpretable additive models via boosting. Okay, what's an additive model? It's a sum of functions of the original variables. So take x1, do a transformation of it, call that f1. Take x2, take a transformation of that, call that f2. And then you add up all these f's, and that's your model. Okay, so why do we care about additive models? Well, additive models are interpretable. That's why they're so elegant, and that's why they're so helpful, because you can figure out exactly, where the kinks, where the important pieces of each variable are that lead to the prediction, and you can really understand how the variables are put together to form the final prediction. And not only that, they're also pretty powerful. Additive models are pretty powerful. And they're also really easy to construct, as I'm going to show you in this video. And in particular, we're going to construct additive models that consist of these piecewise functions, piecewise constant functions. And in particular, these are going to be combinations of stumps, and we're going to get these functions from boosting stumps. Okay, so as you recall from the earlier lectures, in boosted stumps, at each iteration, the weak learning algorithm picks a feature and a threshold, right? These are your weak classifiers. It's like a feature and a threshold, okay? So that's a stump. And then AdaBoost will place a coefficient on it. It'll place a weight on it. All right, so at the first iteration, let's say it picked feature 10 and that particular threshold that I've got there, it's right in the middle of x10. And then AdaBoost weak learning algorithm picked that weak classifier and put the weight alpha 1 on it. Okay, in the second iteration, it picked x3 with this threshold and multiplied it by alpha 2. And also, by the way, if features are binary, then these step functions that I'm creating actually work totally fine for binary features, because they're 0 at 0 and 1 at 1, and that's fine. And you can, if you want to, you can create weak classifiers that are flipped, right? You can have it be 1 at 0 and 0 at 1. Okay, so we keep going like this. At every iteration, the weak learning algorithm picks a feature and a threshold and puts a weight associated to it. And on and on and on. You can see over here, for the fourth iteration, it's picked x2 and it picked a weak classifier that's going down. Okay, so now here's the interesting thing about it. You sort the features. Okay, you sort the stumps by feature. So you take all the stumps for feature 1, you put them in the first row. Take all the stumps for feature 2, put them in the second row, and so on and so forth. And then you add them up, right? You add them up by row. And what you get are these functions. That's f1, f2, and f3. Now, the particular functions I've constructed happen to have some desirable properties, and I want to talk to you about them. Now, this function f1 is monotonically increasing in x1, whereas this one's monotonically decreasing in x2. Now, you can do that by design if you want to. If you actually want a function that's forced to monotonically increase or decrease along the variable, you can force that to happen by limiting the set of weak classifiers that AdaBoost is allowed to choose. So for instance, with x1, so you can make the model monotonically increasing or decreasing for each feature. So for x1, you want to make you want to choose the step functions that only face in that first direction, kind of increasing step functions. Whereas for if you want the f2 to be monotonically decreasing, you allow the weak learning algorithm only to choose these decreasing step functions. And when you add those up, it'll make sure that the monotonicity is obeyed. Because as you know, AdaBoost only produces positive alphas. So, you automatically get the monotonicity because the alphas will always be positive. And so as long as the monotonicity is obeyed in the weak classifiers, you'll get monotonicity in the overall model. Okay, so then you add them up and we've now produced an additive model via boosted stumps. So it's really, really simple. Right, now I'd like to do in notation what we did in pictures a few minutes ago. So here, I have our additive model here, which is written in the typical AdaBoost format, so sum over t, alpha t, ht of x. So ht is the weak classifier chosen at iteration t, which here is a stump, okay? And alpha is the weight on that stump. And then here I have g of y prime. So what you can do if you want is to take the output of AdaBoost, which is that sum there. You can call it g of y prime. And then G might be might be like the inverse of some kind of logistic function like that, so that it forces the y hat to be a probability between 0 and 1, so some number between 0 and 1. So you can interpret the result as a probability. Okay, so let's regroup the terms. As we know, we want to not group the terms based on time. We want to group them based on feature. So let's redo the sum. Okay, so the first thing is that ht, the weak classifier at time t, was a stump. And it's a stump that chose feature j and threshold j prime, theta j prime. All right, so here I chose one that was monotonically increasing, but of course I could have chosen ones that were monotonically decreasing too. All right, so now in typical AdaBoost fashion, we would sum over time and take the weight of the weight alpha t times 1 if we chose that weak classifier at that time. Okay, and then it's alpha t times that weak classifier if we chose it at that time. And then of course I have to sum over all weak classifiers. So in other words, I have to sum over all j and sum over all thresholds. So sum over all features and over all thresholds for that feature. Okay, and then also just to remind you of the AdaBoost notation, if you add up all of the weak classifiers that if you add up all of the times the alpha t's when that particular weak classifier was chosen, that's called lambda j prime. Okay, so just putting it back to AdaBoost notation, we can get the lambdas. Now, putting it back into additive model notation, well, as long as we group by j instead of by t, then we have fj. Okay, so it's fj of xj. Good. So that's our regrouping of the terms, just like I did on the previous slides. Okay, I should mention that boosting is not the only way to train an additive model. There's a way to train it called backfitting, where you iteratively model the residual between y and f, and then you add that to f. Okay, so for instance, you might take y and subtract it from the f that you've gotten so far, and then you look at that residual and try to add another term in there that would minimize that residual. Okay, so you take the residual and you find another term that would minimize the residual, and you make that into ft plus 1. Okay, so I want to talk to you a little bit about some work that was done by Rich Caruana and his team on accurate intelligible models with pairwise interactions. So what I just showed you were pure additive models because just a function for each feature. He likes to also have functions for pairs of features. And he actually has found that this is incredibly accurate for medical data, which are very complex, difficult to work with data. But he's found that these are a really nice balance between interpretability and accuracy. Okay, so he calls these GA2M models, so generalized additive models plus interactions. Okay, so he has these interaction terms where you have interactions between two variables. So here it's k and j. And his algorithm, he has a very sophisticated algorithm for fitting these models, where he fits an additive model first, so no interaction terms, so just fit the additive model, and then all the remainder is what's fit with the pairwise terms. Okay, so he does that until convergence, and then he adds an interaction term, refits the model with the new interaction term, and then continues to add interaction terms, each one chosen to minimize the residual like in backfitting, and then refits each time. So here's an example from their paper where they have two variables that depend on each other, and they produce a very shallow decision tree that would serve as an interaction term for the two variables. Now, he's found some really interesting things in his studies of pneumonia in medical record data, and in particular, I don't know if you can see that, but there's like a jump. Like, it's not smooth. There's a jump at around sort of, 80 something, and there's another, actually there's a kind of even bigger jump around like 68 to 70, right? And so what Rich thinks in terms of that first jump, he thinks that that's a retirement age jump, that if you retire, you actually have a higher chance of dying if you get pneumonia. So somehow there's something interesting that he's figured out that that perhaps retirement is a good covariate that we should be putting into our model, because that might actually have an implication for pneumonia risk. Thanks.